Hello Professor, this is Sujata Ramakrishnan. Today I am going to present a project on design of Ultra Nios 2 instruction subset architecture. Okay, in this project we're going to discuss more about pipelining, what is a pipelining and how do we implement a pipelining. So the main aim of this project is to implement a 32-bit 5-stage pipeline risk-based architecture using Nios 2. Nios 2 is basically a soft-based architecture. So what is a soft-based architecture we will be studying in this case? So in this case, I'm analyzing the instruction format, a data path, and I use the pipeline design. So basically we do the instruction format, we do the data path, we do the control module function, and we do everything and we do it and we simulate it using the pipeline design. And in this case, we are discussing about the 5-stage pipelinings. So the 5-stage pipelinings are the instruction fetch, the decode, the execution stage, the memory access, and the write back. In introduction, we're gonna see about more about the Nios 2 processor. So what is the Nios 2 processor like? The softcore processor is something. The Nios 2 processor is basically a reduced instruction set architecture, and it is a softcore architecture. So what is basically a softcore architecture? It's basically something that can be wholly implemented using a logic synthesis. It can also be implemented via different semiconductor devices which is containing programmable logic. And one more thing is Nios 2, it incorporates many enhancements over the original Nios 2 architecture, making it more suitable for a wide range of computing applications. And it is very simpler to update. And also it acts as a control logic which helps in communicating with the host computer. So basically now we come to the block diagram of the processor, how it works. So in this case we are describing the 5 stages. So the instruction fetch, the decode stage, the execution stage, the memory access, and the write back. So in case of in case of the fetch stage, so what happens is it includes the program counter, the instruction memory, the adder, and the mux. So what basically happens is the program counter, okay, it is going to inherit the memory. The program counter is going to take the value from the instruction memory and it is going to send it to the adder. So every time an instruction is fetched, the program counter is going to be incremented, and it is going to be incremented by 4 bytes. So the value is being added in this case and it is sent to the pipeline register, which is nothing but a latch in this case. So once it goes to the pipeline register, once the program counter value has been fetched, we go to the decode stage. In this case, decode stage is the main intelligence of the pipeline architecture. So in this case, we have a register file which will have the read register 1 and read register 2. So we are gonna basically select 2 registers in this case, and then we're gonna check if we have whatever operations we need to perform, if it's an I type or it's an R type. So if it's an I type instruction which we need to perform, in that case we take help of an sign extend. In this case, in case of sign extend, we'll have the 16-bit. It is going to basically convert this immediate value, which is 16 bits. It's going to convert it into 32 bits. So one of the read register and then the sign extend bit together goes as input to the next stage. So once the inputs has been selected, it is going to the execution stage where it is going to perform the particular operation which is being selected. So if it's an I type, it's going to take the ILE control as help, and it is going to the adder, and it is going to the ALU where it is going to perform whatever operations it is set to do. And if it's an R type, we don't need a sign extend. It is directly going to take the 2 registers and it is going to latch to the pipeline register, and then the execution happens here. So once the execution happens, it's going to the data memory. In this case, if it's a load instruction we are going to perform, in this case the register is going to read the information from the memory address. from the memory. So it is basically, it is going to read the memory access. Okay, so once the memory has been read, okay, how it has to it is going to, the memory is, once the memory is read, okay, the mux is going to select if it's a 0 or a 1. Okay, if there is a memory read, then it is going to go to the right register. Okay, then this way, so that is, the memory is being read, so the load instruction is being performed. So if it's a restore instruction, in that case a write back happens, because the information which is stored in the register, which will be going into the memory. So in this case a write back happens, so which goes from here, and it is basically both of the read and the write, it is going to the register file. Now we're gonna come to the instruction set architecture. Okay, we have three basic types of instructions, such as I type, R type, and G type. I type, it will have immediate 16-bit values, and R type will have will not have a 16-bit value. Instead of that, we have an OPX, which is going to be an extension of this opcode. Next, we're going to have the J-type instruction. J-type instruction will be having a 26-bit immediate value. The I-type instructions is basically used for the load and store instructions. R type is basically used for the arithmetic and logical operations. Say for example add. In this case of I type, we're gonna make use of load and store, etc. So this is a dot vector program which we'll be explaining here. So in this case, move here, this move IA, this particular instruction is basically a pseudo instruction. So what is a pseudo instruction in this case? Pseudo instruction is basically used to simplify the way it is being explained in the program. So mainly we are using it to reduce the number of instructions, as well as it is used in another form. In order to explain a particular instruction in another way, we can use this pseudo instructions. So we're using two pseudo instructions in this case. So it is going to compute the A vector and the B vector, and it is going to store the value of n in the register 4, and we are going to do the load instruction, in which case the value in the memory is going to be stored in the register, and this is the operation which is being performed, and it enters the loop. So once it enters the loop, the various operations is being performed. So basically the value of n is going to be decremented in every instruction. Once every operation is performed, the value of n is going to be decremented. So once this loop instruction is performed, so in the last it is going to store the particular value of R5 in this particular memory address, that is dot product of R2. This is the memory address where the register 5 is being stored. So, and if this if this doesn't work, okay, if this is not complete, it is going to loop back. So until and unless the value of n is going to decrement, it is going to come to 0, until and unless this particular operation is complete, until and unless if it is completely done, it is going to loop back. And so once the instruction, once all the operation is performed, once it comes to 0, then it is going to stop, then the branch will stop. So these are basically the 5 stages of pipelining. In this case, the instruction fetch, decode, execute, memory access, and write back. We've already discussed about it. Instruction fetch, it is going to fetch a particular instruction from the memory. Decode stage, it is basically the intelligence of the pipeline architecture. It is going to decide, it is going to be the control unit. It is going to decide which operation is being performed based upon the opcode which has been selected. And then the execute stage, it is going to perform all the arithmetic and logical operations. Memory access, it is going to fetch from the memory, and it is going to store the data to the memory. So it is going to do a data read as well as data write. And then write back. Write back is something like if there is a load instruction performed, and then it has to read from the register, which is why it is going to do a memory read. And if it's a write instruction, say in case of store, then it is going to do a write back to the write data in the register file. So why, in this case, why do we do pipelining? It's because of the concurrency which has been obtained. So what happens in this case is when a segment completes an operation, it passes it to the next instruction and immediately it fetches the next operation. It does not depend on anything. And next is continuous. It's because it creates a two-stage pipelining where the data read. So why pipelining? In this case, we're gonna do three things mainly: concurrency, the continuous, and the multi-cycle execution. So in this case, concurrency is very important because when a segment completes an operation, it passes to the next and immediately it fetches the next operation. It's not going to depend on anything. Next is continuous. In this case, it is going to create a two-stage pipelining. Say consider there are two stages of pipeline wherein the data read or write can happen in one stage and simultaneously data read and write can happen on the other stage as well. So pipelining, there are like many multiple instructions, multiple data can be fetched, can be written, can be read, okay, at the same time. It is not going to be dependent on one thing to fetch the next instruction. So pipelining is very important. It has huge advantage. So the number of clock cycles are going to reduce in case if we use the pipelining, because many stages, many instruction which needs to be fetched. So one instruction, if it's fetched and it is going to the next stage, the next instruction is going to be fetched by the program counter. So the program counter is not going to wait until that particular instruction which is fetched is executed, it is decoded, and it is read back. So it is going to do the next instruction simultaneously. So some of the simulation output which I have got here, we are discussing about the branch instruction. In this case, in case of branch instruction, mainly what we are going to see is the PC value. If the PC value is considered in this case, then we can say for sure the branch instruction can happen and the branch is being taken in this case. Next, in case of load instruction, in this case we have basically marked all the stages: the fetch, the decode, the execute, the memory access, and we have also indicated the PC value which has been taken and how it is going to be executed, how the particular value, what are the particular operations. In basically in load case, what happens is the read and write, what is the register value, whatever is there in the register value is going to be fed into the memory. So that particular value is, what is a particular value, what is the register value, okay, the value which is stored in the memory, okay, that particular value is being sent to the register in this case. So how does that happen is what we have indicated in this case. The next is a store stage. In this case, we have basically, indicating the value which is stored, the final value which we get. So how is that value being stored in the fetch, the decode, the execute, how it is going to go. The fetched value is being passed through all the stages and it's going to be returned back in the last stage. So the conclusion. How do we conclude is the pipeline which is used in the processors allows the parallel execution of two or more consecutive instructions from a nominally sequential stream. That is, two instructions can happen at the same time. It doesn't have to depend on anything. So it's a big advantage in this case. And also the processor can work on higher frequency with higher throughput. The throughput is really high compared to one which in case of without pipelining, the throughput is comparatively very less. The frequency will have to be very less. But in case of pipelining, we can work on the higher frequencies with higher throughput. Thank you, Professor.